Good day, class. I will be looking at thermodynamics today. We are going to use first law to calculate some examples and what we need to take note in thermodynamics. Then we are going to work on isothermal. We will prove the isothermal formula, and also we are going to calculate many examples under it. Then adiabatic as well. Now, let's calculate from the first law of thermodynamics that says energy can neither be created nor destroyed, but it can be transformed from one form to another. Now look at this. Internal energy is equal to Q minus W. The internal energy here can also be used as the U or the E. Some textbooks use the E or delta E, while some use delta E, delta Q or the U. The same thing. So the U here stands for internal energy, the Q here stands for the quantity of heat in the system, and the W stands for the work done. Now let's use this to calculate some example. Calculate the change in internal energy of the following. 1. The system absorbs 300 joules of heat and performs 500 joules of work. Then we have to calculate the internal energy. 2. The system absorbs 700 joules of heat energy and the surrounding performs 300 joules of 300 joules on the system. Same thing, we have 400 joules of the work is done on the system, and the system loses 200 joules of heat energy. Now, let's solve this one. Solution. Question 1. Let's start from our Q. The internal energy is unknown. Now, if we have to look at this question 1, your internal energy is unknown. We want to look for that. Your Q is 300 joules and your W is 500 joules. But you have to note this. If the system absorbs the heat, your Q is plus. Or if the system gain heat, your Q is plus. But if the system loses heat, it means that your Q is minus. Take note of all this. Same thing. If work is done on the system, your W is what is minus. That is compress. They also use compress for it. But if the work is done by the system, definitely your W is plus. And if the system is expand, it means that your work done is plus. So you have to take note of this. Now, to apply this one, that means here our W also is what is positive. So to apply this in the first law, it will be internal energy is equal to, this one will be 300. According to this one, minus times plus here, you are going to have minus 300 minus 500 joules. Then this one will be internal energy is equal to minus 300 minus 200 joules. This is the answer. Let's try the number 2. The system absorbed 700 joules of heat. It means that your Q, let me write the formula out. Internal energy is equal to Q minus W. Now go to the question. The system absorbs 700 joules. It means that your Q is what? Is plus 700 joules. Now let's try the system. The surrounding perform 300 joules of work. That means your W also is positive, and that should be 300. So joules. To get your answer here, so if you are to apply that here, like plus times minus here, you're going to have minus. That's why this one also is minus. So 700 joules minus 300 joules, that will be 400 joules. Now let's try the third one. 400 of work is done on the surrounding, and the system loses 2000 joules of heat. Now, in this place, if you are to look at your internal energy that you want to calculate is unknown, then your Q, the system loses what? 2000 joules of heat. That means your Q is minus 2000 joules. Now, let's look at W. Your W now is 400 400 joules of work is done on the system. That means your W also is what? Is minus 400. So to apply that in the formula, that will be internal energy equals to minus 200,000 minus open bracket minus 400, so that to be clear. So that this will now be minus 200,000 plus 400, because minus times minus is plus. Then this will now be minus 200,000 plus 400. That will be plus, okay, minus 360,000. 3,600, yeah, joules. That would be 3,600 joules. There's 1,600 joules. That should be one minus 1,600 joules. So this is how to calculate the internal energy using first law of thermodynamics. And you can be asked to calculate any of these one as well. Just make the subject of formula. Now let's move to the isothermal expansion. Now let's look at the isothermal process. It is a process carried out at a constant temperature. That is, and see, the heat in this is the temperature is zero, it's constant. So since the internal energy of the system varies with temperature, that implies that during the isothermal process, internal energy is equal to zero. Now let me go to the first law. Internal energy is equal to Q minus W. So if the internal energy is equal to zero in isothermal, then we are going to have Q minus, we are going to have Q is equal to W. That is, if this one come out of the equal to, I'm going to have Q is equal to W. Now, let's now go back to this process. I want to put something for you in this isothermal so that we are going to get the formula directly. Let's say we have a pot, and inside the pot we apply, let's say there is gas, or let's say we have water, and we try to cover the pot here. By the time we apply heat, or let's say we apply force here, the water is going to, there will be a pressure to the water, and this pot is going to shift up. You can see when you are cooking at times, and the steam will pushing the pot up. So the work has done through that. So the force F make this pot to shift from this position to this place, and the water also will move from here up to this place as well. Then from the cover move from this place to this side, it means that distance has take place, which is D. You can call it delta D or whatever we like. So work has done on this system as we are looking at it. So we can have a formula here to be what? To be W is equal to force times distance, or we say force times delta D if we like. Now, don't forget that pressure applied to this through the force, and we know that pressure is equal to, you can call this one equation 2. You call this one equation, okay, call this one equation 2. Call this one equation 1. So we now say pressure is equal to F over area. So if we are to make F the subject of formula here by cross multiply, we are going to have F is equal to PA. So we'll call this one equation 3. So it means that if we are to apply this one here, we can say W is equal to PA delta D. That is, I substitute for PA in equation 3 into equation 2. Instead of me to write F again, I write PA delta D. So this is how we get a formula for work done to be W is equal to PA delta D. Now, if we are to move further, we know that volume, which is V is equal to length times breadth. Okay, let's say length times breadth times height, or we say distance. It's still the same thing. From here, This one represents area. Length times breadth is area. So we can say V is equal to A delta D, which is this one, distance. So it means that V volume is equal to area times what? Delta D. It's still the same thing. So instead of me to write W is equal to PA delta D, I can, okay, let's call this one equation 4. So I will call this one equation 5. So we are going to substitute for A delta D here to be what? To be W is equal to P delta V, change in volume. So from there we can say W is equal to P delta V. Now, let's now come back to the equation of first law of thermodynamics that says Q is equal to W, or we say W is equal to Q. See the same thing. Now, so far that we have W to be P delta V here, we can say that Q is equal to P delta V. This is one formula to calculate for it in isothermal. So now to name this, we can say this one now is equation 6 as you want. Just make sure that your work is neat from the first to this end. Now say from adiabatic ideal gas, we have P is equal to nRT over V. So in this place, we can now substitute for P in this equation 6 by saying substitute for P in equation 6. So this will now be Q is equal to, now this will now be Q is equal to, instead of P now, we are going to have nRT delta V over V. Now from here, we can derive another formula. So now we are going to integrate delta, either dV or delta V with volume V1 and V2. This will now be Q is equal to integral of V2 V1 nRT over V delta V. From here, then if this integral is going to cancel this, then we are going to have Q is equal to nRT ln, when this cancel this integral, the integral cancel this delta, it will change to ln V2 over V1. Now, don't forget the maximum work done during isothermal process is given as maximum as W max is equal to nRT, so not Q, ln V2 over V1. And remember that from Boyle's law, because isothermal also the same thing as Boyle's law, V2 over V1 is equal to P1 over P2. This equation can also be written as the maximum work done is equal to nRT ln P1 divided by P2. You can put this in brackets. So this is how to derive the formula for isothermal process. Now let's use this one to calculate some questions under isothermal process. Look at this example under isothermal process. How much work is required to compress a molar atomic ideal gas at a pressure of 2.5 exponential 5 Pascal from an initial volume of 0.015 cubic meter to a final volume of 0.10 cubic meter? Now, what is the change in the internal energy of the system if the system releases 350 joules in this process? Now, to get the solution to this one, two things are involved. The first thing is how much work, that is your W, then internal energy as well. So we need to use this one to get the value of W first by saying W is equal to pressure change in volume. Now, our W is not given in the question, we are looking for it. Our The pressure is given, which is to be 2.5 exponential 5 Pascal. Then we are given the volume. The V1 is the initial volume is 0.015 cubic meter, and the final volume V2 is 0.10 cubic meter. From there, you can apply this into the formula by saying uh, W is equal to 2.5 exponential 5 Pascal into bracket V2 minus V1. That is meaning of change in volume there. Then that will be 0.10 minus 0.015. Then by using your calculator, we are going to have 0.10 minus 0.015, and that one will give you about 2.5 exponential 5 Pascal into bracket. The answer of this one is 0.85. So now multiply that one by times 2.5 exponential 5, and this will give you about 21,250 joules. But remember, how much required to compress? When you compress the atomic the gas, I have told you before that that answer will be in what? Will be in minus. So W is equal to minus 21,250 joules. Now you can now use this one to calculate for the internal energy. That's going to the first law that says um, internal energy is equal to Q minus W. Now our internal energy is not given here. Then W is equal to minus 21,250 joules. If our work, and the Q, let's look at the Q, it is minus. Um, the internal energy of the system, if the system releases, when the system release the heat out, then your heat there is minus as well. Your Q is minus 350. So to apply this in the formula, it will be internal energy is equal to minus 350 joules minus open bracket minus 21,250. So this will be minus 350 plus 21,250. So let's press the calculator for this. Minus 350 plus 21,250 joules, and we are going to have 20,900 joules for our internal energy. So this is the final answer. Now let's look at another example. How many work does a gas perform at a constant pressure of 8.4 atm atmospheric pressure as it expands from a volume of 2.0 liter to 4.5 liter? Now you see that the pressure here is not in Pascal, and this volume is not in cubic meter or centimeter cube. So to get this, just a solution, we have to use the same formula to the W is equal to, because they're asking for work done, is equal to P change in volume. So our W is not given, we are looking for it. So P is 8.4 atm, 8.4 atm in bracket. The final volume is 4.5 minus 2.0 liter. So now, if you see, Abi, so 8.4 ATM into bracket 4.5 minus. So if you are to do this in calculator, just say 4.5 minus 2.0. So we are going to have 8.4, which is your pressure, into bracket 2.5 liter. So you have to multiply this now times 8.4. So you are going to have W is equal to 21 ATM liter, or liter ATM. So now you are to convert this one back to joules. So if you want to do that, I just want to give you one conversion rate here, which is very simple. Just remember that 1 ATM liter is equal to 1.013 exponential 5 Pascal. So what you have to do here is just say that 21 ATM liter divided by 1 times 1.013 exponential 5. This one is a constant, it's like conversion rate of units from liter ATM to joules. So over 1 liter of 1 liter ATM. So now this 1 liter ATM will cancel this ATM, then you multiply 21 times this. Then multiply this by 21 by saying 1.013 exponential 5. And this will give you about W is equal to 2,127,300 joules. This is the final answer. Now let's look at another example. An ideal gas initially at 120 degrees Celsius and 2 exponential 5 Newton meter square pressure occupies 8.0 exponential 5 centimeter cube space. Calculate the work required to compress the gas isothermally and reversibly so that the first pressure is 1.5 exponential 6 Newton meter square. Now, if you look at this question, it looks simple and it takes a long process to solve. Now, let us list out the parameters that we have. We have temperature, which is T, to be minus 120 degrees Celsius. If we are to convert this one back to Kelvin, just say minus 120 degrees Celsius plus 273. And this one will give us 153 Kelvin. If you are to press it in your calculator, 153 Kelvin. Now, our volume, we are given only just V1 here, just one V1, which is 8.0 exponential 5 centimeter cube. If you are to convert this one to meters cube, just divide whatever you are given in centimeter cube by 1 million. So 1 cubic meter is equal to 1 million centimeter cube. So that will be 8.0 exponential 5 divided by 1 million meter cube. So an answer here will be 0.8 cubic meter. Sure. Now, let's look at the next one, which is pressure. We are given the initial pressure to be P1 is equal to 2 exponential 5 Newton meter cube square rather. Then P2 is equal to 1.5 exponential 6 Newton meter square. Now, for us to get, so we need V2 in the first place in this formula. Now, before we can use this formula to be NW is equal to nRT ln V2 over V1. So this is normal formula that we're supposed to use, but we don't have V2. So we need to calculate look for V2 the final volume. Now, you know that isothermal is related to Boyle's law. So you can say from Boyle's law that says P1 V1 is equal to P2 V2. So if you are to make V2 the subject of formula here, you're going to have V2 is equal to P1 V1 over P2. So now let's substitute all these values here for P. Then you're going to have V2 is equal to 2.2 exponential. So this will be the P1 should be 2 exponential 5 multiplied by the V1 that has been given to be converted to 0.8, then divide by P2 1 exponential 1 times 5, sorry, 1 times 5, 1.5 exponential 6. Then if we are to apply this into calculator, then you're going to have 2 exponential 5 multiplied by 0.8, and this will give us about 160,000 divide by 1.5 exponential 6, 1.5 exponential 6, and this will give us about 0.106 cubic meter. So our V2 now is this. So now let's now go back to this formula that says W is equal to nRT ln V2 V1. Now another problem that we have here is that if you look at this question, we don't have number of mole. So for us to get the number of mole, we need to go back to ideal gas formula that says P is equal to nRT over V. So if we were to make the number of mole the subject of formula here, then it will be N is equal to PV over RT. So this PV over RT, we are going to substitute it for N in this formula. So this will now be this will now be W is equal to, instead of N, I will say P1, always use the first one, the first pressure and the second and the first volume. P1 V1 over RT, this is my N now. Then RT times RT ln V2 over V1. So RT will cancel RT here. Then we are going to have W is equal to ln P1 V1 times ln V2 over V1. So this is the formula that we are going to use to calculate for work done here. Now come back to these parameters and put the value of P1 V1 ln V2 and V1. So our P1 here is 2 exponential 5 multiplied by V1 is 0.8 converted to cubic meter times ln my V2 is 0.106 divided by my V1 is 0.8. So this will be 2 exponential 5 multiplied by 0.8. I'm going to have 160,000 multiplied by ln, let me write 0.106 divided by 0.8. That will give me 0.1325. So I will just say ln 0.1325 and that will give me about minus 2.0 something. So multiply that by 1,600. 160,600, that should be uh, minus 323,000 800 okay 387.6 joules. So we have to leave the minus because the gas is compressed. So we have to leave the answer with the minus. Adiabatic process. Adiabatic process is one in which there is no exchange of heat between the system and surrounding. It's like isolated system. Now, just keep it in mind from the first law of thermodynamics. We say that delta U is equal to Q minus W. Keep this in mind that in adiabatic process, the heat is constant. That is, your Q is equal to 0. So if your Q is equal to 0, internal energy is equal to minus W. So from here, we can prove this formula further by saying that delta U is equal to, don't forget that our W, we have W to be, W is equal to minus, or let's say P delta V or dV. So now we can substitute for W in this formula by saying minus P dV. And also, delta U, which is internal energy, is equal to, keep this in mind, is equivalent to ZV dt, CV dt. Now, instead of me to be writing delta V, delta U, and then I'll be substitute this CV dt for delta U. That will now be CV dt is equal to minus P dV. So if you like, you can start naming your equation one after the other. So from there, we know that from ideal gas, P, okay, let me write this out. From ideal gas, P is equal to nRT over V. But let's assume that the number of mole here is 1. If number of mole here is 1, that will be P is equal to 1 times RT. So that means that P will now is equal to RT over V. So we can now say CV dt is equal to minus RT. Minus RT, because I have already substituted for P here now. Minus RT over V dV. You can start naming your equation as you like. Equation 1, 2 to any place that the equation will end. Now from here, we can now determine for the value of what? For the value of R. Now, by saying that CV, we have to divide both sides by T. CV dt is equal to minus RT dV, everything divided by V. So if you are to divide these equations by T, then you see that T will cancel C here. Then you are going to have CV dt, CV dt over T is equal to minus R dV over V. So the T have cancelled V here, the T have cancelled T here. So now we can now integrate this one to respect of integral of T2 T1, then this one integral of v1 v2 by saying integral of t2 t1 cv dt over t is equal to integral of v1 v2 minus r dv over v. So if we are to cancel the integral, want to cancel this, that will now be cv ln t2 over t1 is equal to minus r ln v1 over v2. So take minus r to the both side. Then this will be cv divided by r ln t2 t1 is equal to ln v1 over v2. The minus r have cancelled each other here, so there's no more r here. So from here, we can move further by saying r is equal to cp minus cv. Note this, r is equal to cp minus cv. So from here, we can now take this to be ln t2 over t1 is equal to ln v1 over v2 r over cv. What just happened here is that I take this cv over r to this side, and if we are to apply the law of reciprocal, the one denominator will go to the numerator, and the one at top, which is numerator, will become the denominator. This is what just happened here. So from here, we can now substitute for r at this side. That will now be ln t2 over t1 is equal to ln v1 over v2, and this will be cp minus cv divided by cv. So if we are to do it separately, this cp is like cp over cv minus cv over cv. So if cv cancels cv, it will be 1. So that will now implies that ln t2 over t1 is equal to ln v1 over v2 cp over cv minus 1. That is the implication of cp minus cv over cv. So that will now be cp over cv minus 1. So now, there's another thing you have to keep in mind again. Note that cp over cv is equal to this. Is one of the scholars, John Thomas something. So this will now be ln t2 over t1 is equal to ln v1 over v2, then this sign minus 1. So you take the antilog of everything, antilog. Now you take the antilog of both sides. When you take the antilog of both sides, then you are going to have t2 v2 minus 1 is equal to t1 v1 minus 1. So this is the adiabatic formula. So there's a different way to get the formula actually, but depend on the question if you want to solve it. So if you have any question relating to adiabatic, you can put those questions into the comment section. Then I will try to attend to those questions one after the other. Thank you.